Hi, and welcome to our unit on electrochemistry. And of course, like any beginning of any unit in this course, we're going to go to the overall course organization presentation and see where we are in the grand scheme of the year. So I bet you could recite it to me now in your sleep, but remember that our theme for the year is that matter is made of atoms that interact in interesting ways. And here in the last part of our course, we're looking at 4 different interesting examples of specific cases of chemistry. Unit 10 looked at solutions. Unit 11 looked at acids and bases, and here in our second to last unit, we're looking at electrochemistry. We're going to talk about spontaneous electrochemistry, voltaic cells and applications like batteries, non-spontaneous electrochemistry, and electrolytic cells and applications like copper plating pennies and things like that. Does that make sense? Cool. Let's go back to the presentation. To begin our discussions of electrochemistry, we're going to go back to something that we're already familiar with, which is redox reactions, which is really at the root of all of electrochemistry. So let's go in and take a look. Just as a reminder, we learned that the first law of thermodynamics states that energy cannot be created or destroyed, only transformed. We've also learned that any form of energy can be transformed into any other form of energy. The reason we know this is because of work that was done starting in the late 1600s and going up through the 1800s. One of the reasons we know this is because of work that was done in the last 300 years related to electrochemistry. For instance, it was discovered that a structure like this could produce an electrical current. This is what's called a voltaic pile, and what you have here is two different metals sandwiched together with some sort of electrolyte, usually pieces of cloth dipped in seawater. This would produce a measurable electrical current, and so people started to wonder, why is this the case? And it was determined that what we see here is actually redox chemistry. Electrochemistry is fundamentally redox chemistry, and redox chemistry are chemical reactions that produce electrons. Electrochemistry is fundamentally redox chemistry because redox chemistry is the chemistry that can produce electrons. This is actually what's happening in every battery in your life. There's a chemical process taking place inside of that battery. It's a redox process, and so electrons are being produced and used to power the device that the battery is powering. So before we get too far into redox chemistry, we need to remember and refresh our oxidation numbers. We talked about the first 4 of these rules back when we learned about redox reactions in Unit 8. I'm going to add 2 more rules to this list just to help you out, but these 2 extra rules are really not as important as the first 4. The first is that hydrogen is usually given an oxidation state of +1, unless it's in a substance called a metal hydride, unless it's attached to a metal, in which case it's got a -1 oxidation state, as its electronegativity will be higher than that of the metal. And our last rule is that oxygen is usually -2 unless it's in a substance called a peroxide, where it will be -1. Remember that we use oxidation numbers to determine oxidation and reduction. Oxidation is the loss of electrons. This causes the oxidation number to become more positive. Reduction is the gain of electrons. This causes the oxidation number to become more negative. Remember that both oxidation and reduction have to occur simultaneously because charge has to be conserved, just like energy and just like mass. Let's add to our notions of oxidation and reduction by talking about agents and reminding ourselves of spectators. The oxidizing agent is the atom that becomes reduced. It's what causes the oxidation to happen. Similarly, the reducing agent is the atom that is oxidized. It's what causes the reduction to happen. I know it's confusing. I apologize, but we can't do anything about it. Also remember that in many redox reactions we'll have spectator ions, which are ions that do not participate in the redox reaction. Their oxidation state does not change. That's how we know that they're spectators. When we first learned about redox reactions, we just learned about synthesis, decomposition, single replacement, and combustion without really worrying too much about balancing them outside of the traditional ways that we balance equations. At this point, I'd like to introduce another way that we can balance redox reactions, which uses half reactions. A half reaction is simply just the oxidation reaction or just the reduction reaction represented individually. For example, here's a single replacement between iron and copper, and here are the oxidation numbers of all of the species in the reaction. I've put sulfate by itself because it's a spectator ion. Its oxidation state is not changing. If we just wanted to look at the oxidation reaction, we could write a half reaction. Iron 0 yields iron 2+ and 2 electrons. Similarly, if we just wanted to look at the reduction reaction, we could represent it like this. Cu2+ plus 2 electrons gives us Cu0. Those are the half reactions. Notice that in the oxidation half reaction, the electrons are written as a product, and in the reduction half reaction, the electrons are written as a reactant. We can use half reactions to balance redox reactions. In order to do this, we're going to identify the reduction and the oxidation. We're going to write the half reactions. We're then going to balance the number of electrons in the half reactions to conserve the charge. We're then going to balance the equation so that mass and charge are conserved. For us, we're only going to focus on net ionic equations, and we're basically going to ignore balancing redox reactions in acidic and basic solutions. You can deal with those when you move on to college level chemistry or AP chemistry. Let's look at an example of using half reactions to balance an equation. Let's look at an example of using half reactions from our Unit 12 packet on page 7. We'd like to use half reactions to balance the following net ionic equation. So here we see Na0 plus Fe3 plus yields Na plus 1 and Fe0. If you didn't pay attention to the charge, you might think that this is already balanced because we have one sodium in our reactants, one in our products, one iron in our reactants, and one in our products. But that is not correct. Charge has to be conserved. So let's look at the oxidation reaction first. It looks like this. Na0 yields Na plus 1 plus 1 electron. Similarly, our reduction reaction looks like this. Fe3 plus 3 electrons yields Fe0. This is why the reaction is not currently balanced. Sodium is only producing 1 electron and iron is gaining 3. So we need to balance the total number of electrons. To do this, we're going to multiply our oxidation half reaction by 3 and we're going to keep our iron reduction reaction the same. Once we've done that, we can now use the new numbers in order to write the balanced equation. It winds up being 3Na0 plus Fe3 plus yield 3Na plus 1 plus Fe0. Does this make sense? If it doesn't, write down any questions that you have before we wrap up. Thanks so much for watching our discussion of half reactions. Make sure you can do the following things here at the end. Make sure that you can identify reduction, oxidation, the reducing agent, the oxidizing agent, and any spectator ions in a redox reaction. Also make sure that you can represent oxidation and reduction as half reactions. Finally, make sure that you can use half reactions to balance redox reactions. If you can do those things, you're doing great. If not, that's okay too. Take a moment and write down any questions that you have. You can always leave them in the comments below the video, and you can always get in touch with me. Thanks again for watching. I really appreciate it. Have a great day.